Okay, so now we're getting to this section of chapter 10 that not just covers probability, but covers what's called Bayesianism. So this is sort of connecting things back up with real science. So remember this from the previous presentation when we were talking about scientific reasoning. So here's sort of a basic procedure that scientists would go through. You might see this kind of a thing in an introductory science textbook, chapter 1. Here's the scientific method, and they might have a flow chart of sort of what happens. So we start off with there's some specific problem that needs to be solved or some interesting phenomena that needs to be explained. We propose a causal explanation, that is, we provide a hypothesis. Then we generate a prediction that's based on that hypothesis. Then we set up a test to see if the prediction comes true or not. And then we evaluate the results of that test. Does it match the prediction? And then in the previous chapter, we had then what, right? Where do we go from there? And I talked a lot about Karl Popper and his ideas that if the prediction does not match the hypothesis, then that means the hypothesis is false, right? We've used modus tollens, his method of falsificationism, to prove that the hypothesis is false, definitively. Now, Popper also famously said that we can't use induction to support a hypothesis, right? If the prediction comes out true, then that does not mean, according to Popper, that does not mean that the hypothesis is true or even more likely to be true or that we should have more confidence in our hypothesis. He thought that that was bad scientific reasoning. But we then also saw a variety of problems for Popper, that you can't just get a single negative result and then claim that that proves that the hypothesis is wrong, like a guarantee, like we've got a deductively sound argument. It just doesn't work that way. That's not the way science works. It's not the way sort of reality works. But he also talked about that we can't use induction to support a hypothesis, and we didn't really talk as much about why he's wrong there, but this consensus in general among philosophers of science is that he was wrong about that as well, that we can indeed use positive evidence, that is, when the prediction turns out to be true, we can use that to say that we have more confidence in our hypothesis now than we used to, or that the probability of the hypothesis being true has gone up. And so that's where Bayesianism comes in, because we should then ask, well, by how much does the probability of the hypothesis go up? You know, it's easy enough to say that, oh, we should be more confident now than we were before the evidence came in. Or maybe we'd say that we're less confident, right? If we get a negative result, but we don't want to go so far as to say that the hypothesis has been proven to be false, nevertheless, we might say that our confidence in the hypothesis being true has gone down. But by how much exactly? Right? How should we change our probability assessment based on some new evidence that's come in? So that's what Bayesianism is all about. And it uses some of the stuff on probability that we showed up earlier in this section, chapter 10, section 4, and builds it together to show us how to update probabilities based on new evidence. Okay, so pretty simple starting out here. We just use capital H to represent the hypothesis, capital E to represent the evidence. And so, in a sense, what we're doing here is just a simple conditional probability. You know, what's the probability of the hypothesis given this evidence that we just got? And so, the problem, though, is that doing this in sort of a real life situation, in a real scientific situation, starts to get a little bit complicated. So let's build up to that. And in order to do that, we need this concept. This is central to Bayesianism, this idea of a prior probability. Right? So before you do any of the testing, before you gather any evidence about anything, you don't hear anything about whatever, just based on what you already know, before you start doing the testing or start gathering any evidence, based on what you already know, what's the probability of something being true? So what's the probability of the hypothesis being true or the evidence being true? All right, so these are the things we need. What's the prior probability that the hypothesis is true? And if it's something you just really don't know anything about, one way or the other, you could use the principle of indifference here. Just give it a 0.5 probability, 50% chance of being true. We'll also need to know the probability, the prior probability of the hypothesis being false, and that's easy enough. You just use that negation rule. So it's just 1 minus the probability of the hypothesis being true. Then we'll also need to know the prior probability of the evidence being gathered, right? The prior probability of, in this case, the prediction coming true. Just a little bit more to say about that. If you're not going to use just the principle of indifference to establish the prior probability of the hypothesis being true. It could be that we're dealing with a very well-established hypothesis, something that pretty much everybody already believes is true. So we put the prior probability of that really high. We don't want to put it at 1 because we're still talking about science here, and science always has to acknowledge that we can't get all the way to 100% guaranteed that our hypotheses are true. So, but we might set it pretty high, so 0.95. That's a pretty high thing for a well-established hypothesis. But it could be some really new, exciting, interesting thing, some new, maybe seemingly kind of crazy new suggestion that some scientist has come up with. So in that case, we might say, all right, that's interesting, and we'll do a test on it, but we're not very confident that that hypothesis is true. So we might put the prior probability pretty low, like a 0.1. Okay, then we could say some more about the prior probability of the evidence being true. Well, if this is something we've seen many times before, so let's say we're talking about Einstein's theory of general relativity. Back in the early 1900s, people were not very confident that theory was true. In fact, they thought it probably was not true. So let's say that then Einstein's general theory of relativity is generating these predictions, and one of the predictions is something simple, something that we've already seen before. So according to Einstein's general theory of relativity, this pen, when I release it, it should fall to the ground. It should fall straight down. Well, yeah, we've seen that millions of times before. The old Newtonian theory that had been in use for hundreds of years predicted the exact same thing. So it is very unsurprising, right? So the prior probability of that evidence being gathered, that pen will fall down, well, that's really high, right? We put that at like 0.99. And this is where it gets more interesting, is that if we've got this hypothesis, some new theory or something, that predicts something surprising or really unexpected, then we put the prior probability of that evidence being true really low, right? Because it's something we've never seen before, or something that's unexpected, maybe even something that based on our previous knowledge we suspect just isn't going to happen. Then we put the prior probability of that evidence really low. And that kind of lines up with this quotation that is attributed to Carl Sagan, this idea that extraordinary claims require extraordinary evidence. And as we'll see, sort of the Bayesian approach here captures that idea, that if we've got some really new, kind of seemingly sort of crazy new hypothesis, like Einstein's general relativity when it was first proposed, we'd say that's pretty unlikely, right? That's an extraordinary claim. So in order to support that, we need to look for some really extraordinary evidence, something really new and surprising. And you might remember from a previous presentation that one of those was that light, the path of light will bend when it goes through a strong gravitational field, even when it's empty space, right? Because Newtonian theory says that light will always travel straight through empty space, but Einstein predicted that the path of light would bend if that path of light is going through a strong gravitational field. Okay, so it seems at first like we're just dealing with conditional probability. What's the probability of the hypothesis being true given that we just gathered some evidence? But the problem is that, one of the problems is that the truth, the probability of the hypothesis being true and the probability of the evidence being true, those things are sort of intimately intertwined in a complicated way. So we can't just use this simple conditional rule that we saw from the previous presentation, but that's at least a starting point. So let's start there. All right, the probability of the hypothesis being true given the evidence. Well, here's the conditional probability rule. We just have the probability of the hypothesis and the evidence both being true divided by the probability of the evidence being true. And by the way, we're talking about prior probabilities here. So what's the prior probability of the evidence and the hypothesis both being true divided by the probability of the evidence being true? Then when we apply that conditional rule, well, when we convert that using the general conjunction rule for the numerator here, right? This is probability of the hypothesis and the evidence. So we've got an and, so that's a conjunction. So then and they are not independent, right? They're sort of intertwined in a complicated way. So we can use the general conjunction rule to figure out how we deal with that, right? So that converts the numerator, right? The probability of hypothesis and evidence becomes this. It's the probability of the hypothesis multiplied by the probability of the evidence given the hypothesis. So that's our numerator. Then it's divided by the probability of the evidence. Well, that's also complicated because now we need to figure out what's the probability of this evidence being true, right? Being gathered if the hypothesis is true. But then we also need to figure out what's the probability of gathering this evidence even when the hypothesis is false, right? So even if it turned out that Einstein was just wrong, right? His general theory of relativity, maybe it turns out it's just false. Nevertheless, it could be for independent reasons. Light that's going through a strong gravitational field will bend even when it's going through empty space. So we need to account for that possibility too. So the probability of the evidence being true sort of expands out into this somewhat long, complicated formula here. So that's the actual denominator that we need to add in. So when we put it all together, it looks like this. What's the probability of the hypothesis being true given that we just gathered this evidence? Well, it's all of this. And it looks like sort of a big complicated mess, but there's not any fancy mathematics really going on here. As long as we keep track of the values that we're plugging in for all of these things here, the mathematics is actually relatively simple. So let's look at what I hope is sort of a simple example. It's the coin flip example. And so our hypothesis, let's just say that for whatever reason, I'm predicting or I'm hypothesizing that this coin will land heads up. Let's just say that that's our hypothesis. Sort of a weird hypothesis. It's not a sciencey real hypothesis really, but we're just using this as an example to work through the formula. So what's the prior probability that that hypothesis is true? Well, you know, without gaining any other information, I'm just given a coin and I'm hypothesizing that it's going to land heads up. What's the prior probability that that's true? 0.5, right? 50-50 chance. Just apply the principle of indifference there. Now let's say that I'm told now that this coin has been manufactured to be fair. In fact, maybe I even visit the coin manufacturing factory and I review sort of all the machinery and so on, and it's like, yep, looks like this is the manufacturing process is good, and so the coins coming out of this factory really are fair. So there's really only a very small chance of manufacturer defect. So let's say that that's the situation. Well, like I said, the prior probability of the hypothesis being true, that that the coin's going to land heads up, that's 0.5. And then, of course, the prior probability of the hypothesis being false is also 0.5. Right? It's just 1 minus the prior probability of the hypothesis being true. What's the prior probability of this evidence? Really high. Like I said, I went and visited the factory and everything, so really, really high probability that this evidence is actually true. So it's going to be 0.9 whether the hypothesis turns out to be true or not. So the prior probability of the evidence given that the hypothesis is true, 0.99, the prior probability of the evidence given that the hypothesis is false, right, that the coin actually lands tails, then that's also 0.99, right? So then the prior probability, before we run through the calculations, if we're just sort of intuitively thinking about this, the prior probability of the hypothesis being true given this evidence, it should work out to 0.5, right? If we're working through the calculations correctly and we've got a good formula, then it should turn out to be 0.5. Well, here's those numbers that I had in the previous slide. Here's the Bayesian formula. We plug in the numbers, and if you feel like running through the calculations, feel free. And it does indeed work out to be 0.5. Okay, so let's look at something that's at least a little closer to something that we might see in science. So we've got these two jars of marbles. And let's just say that like I put the marbles into these jars, so I know exactly what's in them. And jar A has 70 red marbles and 30 blue marbles, whereas jar B has 20 red marbles and 80 blue marbles. Then I go into another room and I have somebody pick a marble. And so what's the chances of that marble coming from jar A or jar B? Well, there's only two jars here, and so before I get any other information, I just apply the principle of indifference, right? So I give it a 50-50 chance. So the prior probability of any marble being drawn coming from jar B is 0.5. But now let's say that somebody actually does this and they bring me the marble and I see that the marble is blue, right? So now I've got some evidence that I need to take into account. So now I would ask, like, what's the probability that this marble came from jar B, given that this marble is a blue marble? Okay, so what are the values for all the prior probabilities here? Well, like I said, the prior probability for just the hypothesis on its own, independent of any evidence I might gather one way or the other, I've only got two jars, so it's a 50-50 chance that it came from one jar versus the other. Same thing for the prior probability of my hypothesis being false. Remember, my hypothesis is that the marble did indeed come from jar B. And again, before I get any evidence, it's just 50-50 either way. Now, what's the prior probability of the evidence? Well, we need to do it in two ways. What's the prior probability of the evidence given that the hypothesis is true? That is, given what's the prior probability of having a blue marble given that the marble was indeed drawn from jar B? Well, that's 0.8, right? Because we know that there's 80% of the marbles in jar B are blue. So the prior probability of getting a blue marble from jar B is 0.8. The prior probability of getting a blue marble, if it's not from jar B, that is, it's from jar A, well, that's 0.3, because we know from up here that the jar A contains 30% blue marbles. So that's how we get sort of our numbers here. Let's plug the numbers into the equation. Feel free to work through it on your own if you want, if you don't trust sort of what I've got here. Well, it turns out that the probability that this marble that I just got, which is blue, came from jar B is about 0.73. Okay, big deal, like we just figured out something about these marbles in jars. Well, the thing that's interesting perhaps about this is that if you just look at this information and you see that the evidence is that the marble is blue and the hypothesis is that the marble is drawn from jar B, very few people can sort of intuitively jump to the conclusion without working through the mathematics, just intuitively recognize that the probability that this marble came from jar B is 0.73. Most people need to actually run through the calculations to get to a number like that. Okay, so we're going to look at a couple of other examples here just to sort of see Bayesianism in action. And this is a more realistic and maybe more important example. So let's say that there's some disease out there, and maybe it's a somewhat nasty disease, and it turns out that this disease, the treatment for it is also very difficult, right? It's very unpleasant. You definitely don't want to go through this treatment, so the example says. You don't want to go through this treatment unless you're sure you have this disease, or you have very high confidence that you have the disease. Now, what are the numbers? Well, let's say that this, just in general, for the whole population of people, of which you're a member, it affects about 1% of the population. So that's the background rate of the disease in the population. And now we've got this test for the disease. And we know that this test is not perfect. That is, the test has a false positive rate of 2%. That is, 2% of positive results come even when people don't have the disease. The false negative rate is 3%. So that means that 3% of the time that the test gives a negative result, 3% of those times are times when the person really actually does have the disease. So the test missed it. So now the hypothesis is that you have the disease. And the evidence, let's say, is that the test did indeed come back positive. So the question is, should you go ahead with the treatment? Well, you know, unless you've got a lot of experience with diseases and testing and false positive rates and negative rates and sort of how you should update your confidence in your hypotheses and so on, it could be hard to see. You might say, oh, my test came back positive and it's got a false positive rate of only 2%. That sounds pretty good. There's a really good chance I've got the disease. Well, let's look at the numbers, right? Let's actually work through the equation here. So the prior probability of the hypothesis being true, remember the hypothesis is you have the disease. Well, the background rate of the disease, we already said, was only 1%. So that's 0.01. So that's a pretty low prior probability. The probability of the hypothesis being false, well, that's 1 minus the probability of it being true, so that comes to 0.99. The probability of getting the evidence if the hypothesis is true, that's 0.97. It's not 100%, right? Because we know that there's a false positive rate. But what's the false positive rate? Or what's the known positive rate? Well, it's 1 minus the known false negative rate. Right? So if you get a positive test, what's the likelihood of getting that positive test if you actually do have the disease? Well, that works out to 0.97. But what's the probability of getting a positive test if you don't have the disease, right? If the hypothesis that you have the disease turns out to be false? Well, we already were told that the false positive rate is 0.02. So that's what we put in here, right? That's the rate at which we get a positive test even when you don't have the disease. So that's 0.02. Okay, now we take those numbers and we plug it into the Bayesian equation. Feel free to work through it on your own if you want, but it turns out the number we come up with, that is the probability that you have the disease given that the test came back positive, it's only 0.329, right? That's pretty low, perhaps surprisingly low, given the fact that this test seemed like it was a pretty good test, right? False positive rate of only 2%, that sounds good, but if the background rate of the in the population of people who have that disease is really low, it's only 1%, then even if you get a positive test, the chances of you having the disease is only about 1/3, right? 0.3. So do you like those odds? Are you going to go through with this really difficult treatment? Well, maybe that's not convincing enough. So maybe you should go ahead and get tested again. So let's do it again. Repeat the test. But now we use the probabilities that we calculated from the first test. So now, rather than starting with a 1%, 0.01 is the prior probability of the hypothesis being true that you do have the disease. Well, now you've got some updated probability based on that first positive test. So now the prior probability that you have the disease is what we calculated before. It's about 0.33. And then now the new evidence is that the second test comes back positive as well. So what are those numbers? Well, prior probability of the hypothesis being true, like I said, we just calculated that based on the first test, 0.33 approximately. Prior probability of the hypothesis being false, well, that's just 1 minus the probability of the hypothesis being true. And so that's 0.671 in this case. These other numbers stay the same, right? The false positive rate and false negative rate of the test are unchanged. So those are the same numbers we had the first time through. All right, plug that in. What do we get? Well, now, after the second round of testing comes back positive, now it turns out that the probability that you have the disease is up to 0.96. That's pretty good odds that you have the disease. And now that seems like pretty good justification for bothering to go through this maybe very difficult or very expensive treatment process. Okay, so this shows the value of repeat testing for diseases that the initial probability of you having the disease is pretty low. And this is why medical experts discourage people from just getting general tests, right? Don't just start getting tests for everything. Only get a test for a disease or a disorder or some problem, some medical problem. Only get tested for it if you have some reason already for thinking that it's likely that you've got that problem or you've got that disease. Because a lot of medical problems, even the really severe ones, they tend to have a pretty low background rate. You know, like what's the background rate for cancer or something? Pretty low overall. I mean, there's a decent number of people that get cancer and we should be concerned about that. But you don't want to just like go to the doctor and just start getting tested for all these different kinds of cancer, because all of those tests have a non-zero false positive rate. Right? So that if you get a positive result, that does not automatically mean that you have that disease, right? You have that kind of cancer, you have that disorder or whatever it is. This shows us, right, the first round when we went through it, even if it comes back positive, and even if it's a pretty good test, if the background rate of the disease is kind of small, then this still doesn't give you that good a reason for thinking that you actually have the disease or you actually have that medical disorder, right? So don't just start testing all over the place, and then when you get a positive result, be convinced that you've got that problem. That's bad reasoning, and it's hard to see that that's bad reasoning unless we actually calculate out the real probabilities here. So that's one of the big values of Bayesianism here, using this formula to really get a sense of what the real probabilities are. And it also shows the value of repeat testing, right? If the test like this does come back positive and you're worried about it, get a second test or get a second opinion from another doctor. Because if two doctors agree that you've got this problem, then the chances you really do have the problem go up by a lot. If only one doctor does, well, you know, maybe. It's not, you shouldn't have as much confidence in the opinion of one doctor as you do in the agreement of two doctors. Same thing with testing. You shouldn't have as much confidence in a positive test, a single positive test, as you do in two positive tests. Then if you did a third one, well, this probability, if a third one comes back positive, the probability goes way up, you know, 0.9999 something. Okay, so yeah, this is what I've already been saying. Repeated testing is important, but this is also the case that we talked about this, how new evidence, new and surprising evidence when we're talking about a scientific hypothesis like Einstein's general relativity. This new, unexpected, surprising evidence has a somewhat big impact. However, remember when we were talking about Karl Popper, and he was using that Eddington expedition where they did try to see whether starlight, the path of starlight, bent when it went through the strong gravitational field of the sun? Well, it turns out that the observation contradicted the old, very well-established Newtonian theory, and Popper wanted to say, well, therefore the Newtonian theory is false, conclusively proven that it's false. And we saw why that's problematic. You can't really jump all the way to that extremely strong conclusion. But Popper also said that hanging on to the old theory in the face of negative evidence, that's irrational, right? That just shows that you've got this irrational emotional attachment and you're not being sort of a tough-minded scientist. So was he right about that? Well, let's take a look, right? Let's work through the Bayesian formula here for that. So let's first do it from the Newtonian perspective, right? So the hypothesis that we're talking about is Newton's theory. Well, like I've said multiple times, Newtonian theory had been around for centuries, very well established, seemingly very reliable. So people had a very high confidence that the Newtonian theory was correct. So the prior probability of the Newtonian theory being correct, really high. The prior probability of it being wrong, very low. The prior probability of this evidence being gathered, right, that the light doesn't go straight, people didn't think that that's what was going to happen. So the prior probability of this evidence was pretty low. So what are the numbers here? Well, you know, it's hard to come up with exact numbers here, so I'll give like some rough estimates. What's the prior probability of the Newtonian theory being true? Pretty high. Let's say 0.95. So the prior probability of it being false, 1 minus the probability of it being true, so 0.05. What's the probability of getting the evidence if Einstein's theory is true? I'm sorry, what's the prior probability of getting this evidence of the bending light if Newtonian theory is true? So it's not expected to happen, right? We expect that the light will go straight, but we have to acknowledge it's not impossible. We don't want to set this at 0, so let's give it a pretty low number. Let's say 0.1. Then what's the prior probability of getting the evidence if Newtonian theory is false? Well, that doesn't automatically mean, you know, if Newtonian theory does turn out to be false, that doesn't automatically mean that Einstein's prediction of the light bending as it goes through the strong gravitational field of the sun, that doesn't automatically mean that Einstein's prediction is going to be true. And so people were still pretty skeptical. They had never really thought about, you know, the path of light bending in this way. So let's just leave it at the principle of indifference, just because we don't really know for sure one way or the other. So let's put it at 0.5. Okay, now plug it into the equation, right? Use those numbers that we got from the previous slide and plug it into the Bayesian equation. What do we get? So how likely, once we see the light path of the light did bend, how should we update the probability of Newtonian theory being true? Well, it definitely went down. It started at 0.95 and came all the way down to 0.79. But 0.79, that's still pretty good odds, right? Or about an 80% chance of being true. So that certainly doesn't show that it's conclusively proven that Newtonian theory is false. In fact, it's still got a pretty high probability of being true. Okay, so let's do the same thing, but from the Einsteinian perspective. So now the hypothesis that we're dealing with is Einstein's theory of general relativity. Well, it was very new, very strange. People were very skeptical about it being true. They thought it was pretty unlikely to be true. So our prior probabilities should reflect that. The prior probability of Einstein's theory of being true, low. Let's give it a 0.05, right? Extremely unlikely. So then the prior probability of it being false, high, right? 1 minus the probability of it being true. So the probability of it being false, according to sort of people's minds at the time, 0.95. Now, what's the prior probability of getting this evidence of the bending light if Einstein's theory is true? Well, that's high, right? That's sort of a fundamental prediction of Einstein's theory. So if the theory really is true, then there should be a pretty high probability of getting this evidence. Not perfect probability, you know, it's not 100%, but pretty high. So let's put it at 0.9. What's the probability of getting this evidence if it turns out that Einstein's theory is not true? Well, then we just default back to what we had for Newtonian theory, right? What's the probability of getting this bending light evidence even if Newtonian theory is true? Low. Let's put it about 0.1. Okay, so plug in the numbers. What do we get? Well, for an extremely unlikely to be true theory, like Einstein's theory of general relativity, even when we get the evidence coming in, evidence that we thought was very unlikely, it's very surprising, kind of shocking evidence, well, that only raised the probability of Einstein's theory being true to 0.32, right? Raised it a lot. The prior was 0.05, and it raised it all the way up to 0.32, but it didn't even get it to 50%. So is it irrational for the supporters of Newtonian theory to hang on to Newtonian theory and still be kind of skeptical of Einstein? No, it's not irrational. In fact, it's perfectly rational given the numbers that we just got here. To completely abandon Newtonian theory and latch on to Einsteinian theory after this one result, that actually would have been irrational. And so it made sense for the scientific community to have some resistance to accepting this new crazy Einsteinian general relativity in the face of this one observation. Now, it did turn out that later on, there were some other things that were pretty extraordinary predictions from Einstein's theory that were incompatible, that Newtonian theory did not predict. Things like black holes, other weird things that maybe you've heard of, like gravitational lensing or time dilations. These are things that Newtonian theory does not predict, but Einsteinian theory does. And they're sort of crazy new things that nobody thought would actually come true, but they did come true. In fact, even Einstein thought that there couldn't be any such things as black holes. So he put the probability of that evidence, even if his hypothesis is true, he put the probability of that pretty low. But it turned out it's true. There's such things as black holes. We got that evidence. And so this repeated evidence coming in over and over again in favor of Einstein's theory and over again against Newtonian theory. Well, this shifted things quite dramatically. And so now the scientific community does, in fact, accept general relativity as being the better theory. And they've now, no, it doesn't quite seem this way. Newtonian theory still has a lot of use to it. It's a very useful theory, but it turns out that by and large, the community of physicists believe that Newtonian theory is actually technically false. And they've replaced it with general relativity. Okay, so this gives you a sense of how Bayesianism works, sort of in artificial examples like the marble example and so on, but also in real examples like medical testing and physics. All right, so this is a complicated topic in some ways. It's complicated to sort of intuitively recognize how new evidence should affect our confidence in the truth of a hypothesis. So work through various alternative numbers for the prior probabilities. Definitely work through the problems in the book just to kind of get a sense of it. But I will stop there.